I have your notes here for day one of limits. This is, it's actually part of the pre-calc curriculum. But my goodness, the importance this has for those students going into calculus, whether you're going into calculus here at FC or you're going into calculus at some point in college. The foundation of calculus, like what it's all based on, is limits. So we want to make sure that you get a good foundation in limits. You understand what they are, how to find them, things like that for going on to higher level math. So this is what a limit problem is going to look like. It's gonna, and you need to know how to say it. So as you're reading a problem, this is what needs to be going through your mind. And there's kind of two ways to do this. The limit of f as x approaches a is equal to, and then whatever answer you might get. Or the limit of f of x as x approaches a is equal to, or the limit as x approaches a of f of x equals whatever your answer is, okay? So as long as you're saying limit, as long as you're mentioning the function that you're taking the limit of, no matter how you call it, you can call it f or you can call it f of x. I'm taking a limit of this function as x approaches some number. This number is going to be specific. This isn't going to be an a most of the time. This is just helpful to kind of teach you what a limit is. So this number is going to be an x value. Think about that. You find x values along your x-axis. As x approaches some x value along the x-axis, our answer, this is going to be a y value. Some y value. Now keep in mind, y values determine the height of your graph. So when you're looking at a graph and your graph gets really high, we can say, oh, those y values are getting really high. Okay? So this is going to be an x. This kind of determines our left-right direction. Where are our eyes going, left to right? This, our answer, is a y value. How far up do we have to look to find our function? Or how far down do we have to look to find our function? Where is the graph at that point? Once we get our eyes to the right, left, right spot, then we have to choose the right up, down movement to determine, I need to go hunt down that graph. Where is it? How far up do I have to look, or how far down do I have to look? Okay, so a couple of pictures. They look the same when you take a really quick glance. They look the same. However, they're not. In the first graph, I just want to point out the function is pink. See how high it gets? See how low it gets? See how high it gets? Do you see how as I'm talking about these, my x's are progressing in the bigger direction, right? So right back here, x values are negative, correct? Here, x is 0. Over here, x is positive. And my x's, the farther right I move on the graph, my x's are getting bigger and bigger and bigger and bigger. What's happening to my y's? Well, they're getting bigger, now they're getting smaller, now they're getting bigger and bigger and bigger, okay? So, check this out. On this pink function, I want us to kind of focus our eyes in this area right here, this general area, and I'm going to point out that there is a filled-in point on the pink graph right here. So there is a point that exists. There is an ordered pair that has this for an x and this for a y. It's there. Next graph. What do you see? Ah, look, there is no point right there like there used to be. So I'm going to say there is no point on this function. There's no ordered pair called a comma l. Is there an a comma something? Well, in this case, yes, there is. Right? This is just a piecewise function. Not a big deal. You've seen piecewise functions before. So yes, there's this pink function, but all of a sudden, at a, there's a point down here. So there is a point called a comma something. It's just not a comma L. No big deal. Okay? And then over here, same function. There's no point here. It's an open circle. So there is no point a comma L. We say, oh, and there is no point anywhere else. So there is no a comma anything. There's points all along here, all along here. There's points, there's points, there's points, there's points. There's no point here. No big deal. There's just no a comma anything. So we say f is undefined at a. F has no y value at a. That's what that means. Now, here's the cool thing about limits. When we're doing a limit, remember how I said I want you looking in this general area? Okay, so when I'm doing a limit, I really don't want you to look at this point right here. I don't want you to look there. I want you to look near there. Near it. Not at it, near it. So, here's what a limit is. You ready? The limit of f as x approaches a. So, when I look at the graph, my eyes, in the left-right direction, my eyes are kind of going to narrow in on this x value. Okay, so I really don't want to look over here at the graph. I really don't want to look out here at the graph. I kind of want to look at the graph right around here. Now, the limit says, now that you know where to look, go find your function. Is it down here? No, it's up here. Okay, now, some of you might go, oh, look, there it is. I don't want to know what it is right there. I want to know as I'm close. See, close on the left of this point, close on the right of this point. These y values right here, what are these y values close to? Well, you can say, that's silly, Ms. Neal. This y value right here is L, whatever that is. This y value is L. So these points, these y values right around it are going to be L. True. So as x is close to a, y is close to L. Thus, the answer to my limit. As x gets close to this number, y gets close to this number. Look at the next picture. It might make a little more sense on this picture. Ready? Limit of f of x as x approaches a. So this tells me where my eyes need to go. Do I want to look over here? No. Do I want to look? No, I want to look right here. Ready? Go find your function. Well, here I go and I found a point, but I'm going to look at f. I'm going to look at these up here because here's the thing. I know that at a, the y value is lower than L. But when I do a limit, I don't want what's happening at this. I want what's happening near it. So I don't want at x equals a. I want as x is close to a. So where is x close to a? So let's look really, really close to it, not on it, close to it. Where's the pink? Where is the pink graph when I'm close to it? Well, the pink graph is right up here. So as x is close to a on this side, and as x is close to a on this side, what are my y values close to? L. The limit as x approaches a of f of x is L. As x gets close to a, my y's are getting close to here. A limit is not about what's happening at a. It's about what's happening close to a. And last one. Same picture, only there is no actual point at a. But you know what? I don't care. Because when I'm doing a limit, I don't care what happens at A. I want to know what happens near A. So it's the same problem. It's the same answer. As x gets close to A, go find your function. These y values and these y values are close to this y value. So the limit as x approaches A of f of x is still L. It doesn't matter if the function is undefined at A, if the function has some other y value at A, or if the function is just fine at A. It doesn't matter. We're looking at what's happening around it, not is there a point there. Okay. Kind of the same, we're going to kind of look at the same thing, but in an algebraic standpoint, sort of. Does anybody know what, without using your graphing calculator, does anybody know what the graph of this function looks like? I bet you don't. So maybe you might be able to consider what the graph looks like if I factor it for you. So this is the factored form. I'll let you see them both at the same time. This is the factored form for this function. Now, most of you could look at this function and say, hey, I don't know what the graph looks like, but something's going on at x equals 2. And if you think back to first semester pre-cal, do you remember this? You know something's going on at x equals 2, but is it a hole or is it a vertical asymptote? Those were our two options. When we know f blows up when x is 2, how does it blow up? What's it look like on a graph? There's either a hole there or a vertical asymptote. It depends on what your numerator looks like. So I factored the numerator. Do you see how this x minus 2 matches this factor of x minus 2? Do you remember what that means as far as is it a hole or is it a vertical asymptote? There might be a couple of you that remember. When you see them and it looks like they could cancel, there's a hole there. When you see this factor, when you see this repeated up here, there is a hole at x equals 2. So, here's what I'm going to have you do. You're going to think cancel. I'm going to say ignore the hole, because the hole is what's making this function blow up at 2. I'm going to say ignore the hole at x equals 2. What's left? Okay, so you've got this ginormous graph. You've got all these x values, and you can't really find out what's happening here because you've got this hole that's in your way. It's like looking at the sun. It's like all you can see, but there's so much else out there. Stop looking at the sun, okay? Stop looking at the hole. What else is there? Ignore the hole. What else is there? Well, there's a quadratic equation. My graph is a parabola with a hole at x equals 2. See? Now, this is zoomed in quite a bit, but you can kind of see the shape. Looks like a parabola, and look, there's a hole at x equals 2. Check out the height of this hole. How high up on the graph is it? Somewhere between 10 and 15, right? So here's the thing. I think there's a missing point in my function. I believe there's a 2 comma nothing. There is some y value that can't be, because the x value that wants to make it happen makes the function blow up. So here's what I did. And just look at the table right now. I do kind of want you to pause and copy some of this down, but hang on. I'll give you a chance to do that. Check out this table. So literally, I typed my function in my graphing calculator and went to table. And when I set up my table, I set my table set to ask. So I could type in these decimals. I could type in 1.75 for x, 1.9 for x, and so on. So when x is 1.75, this is the y value that it gave me. Okay, look, see how my x's are getting closer and closer and closer to 2? Where are my y's headed? 10.5, 11.41, 11.94, 11.99. Can you all see that coming from underneath the function, below the function, my y's are headed, I think, toward 12. Do they ever reach 12? Nope, the function blows up at 2. What about on the other side? So how about on the other side? See these x values? 2.25, 2.1, 2.01, 2.001, 2. Do you see how my x's keep getting, I'm like backing down closer and closer and closer to 2. As x gets close to 2, what are my y's getting close to? My y's are getting closer and closer to 12. So they're getting higher on this side, closer and closer and closer to 12. They're getting lower on this side, closer and closer and closer to 12. But is there actually a y value of 12? No, because the function blows up at what would be 2, 12. That's when the function blows up. Okay, so we say there's a hole at x equals 2. We can also say xf is undefined at x equals 2. And just to reiterate, with limits, we really don't care about this. We care about what's happening here and what's happening here. Near x equals 2. Pause it, copy that down. Okay, now, before we get into actual problems with a graph, I just want to limits get a little more specific. So, I'm going to zoom in on this. You've already seen this notation before. This is going to be a little bit different. This is going to say the limit of f as x approaches a from the negative side, right? So if you're looking at a graph, where are negative x's? They're that way. So as x approaches a from the left, And then we're also going to look at the limit of f as x approaches a from the right. Now, let me show you visually what that looks like. So let's say, whether there is or is not a point, I don't care, but let's say there is. Let's say that for this x value, this is the height of the graph, and it's a comma l. Ready? We're going to be doing a limit as x approaches a. So this kind of tells you where your eyes need to look. However, we're approaching a from the left. So my eyes have found a, but now my eyes are going to jump to the left of it a bit. And I'm going to move in toward it. Okay? So first of all, I'm just going to show you the x movement. Here's a. I've jumped to the left. My eyes need to do this. My eyes need to progress toward A. My eyes need to progress toward A. Now, as they do that, I want to follow the height of the graph. So I've jumped to the left. Here's the height of the graph. Let me make this a little more reachable. I've jumped to the left. Here's the height of the graph. Ready? I'm moving toward A. My eyes are moving toward A from the left side of it. Where are my y values headed? Where is the height of my graph headed? It's headed toward this y value. So the limit from the left, my y's are headed toward this y value. Next one, let's do the limit from the right. Again, Whether there is a point here or is not, I really don't care, but okay, whatever, I'll make one. Let's do the limit from the right. Ready? The limit as x approaches a. So where do my eyes need to be? Well, it's all about a, but this told me to jump to the right of a. So my eyes are going to jump to the right of a, and I'm going to move backwards, closer and closer and closer to a. As I do that, I'm going to watch the height of the graph. Where is the height of the graph headed as my eyes move closer and closer and closer to a? The height of the graph is headed toward this y value. Right? The height of the graph was higher than this y value for a while, but it came back down and it was headed toward this y value. So why is that important? Why do we have to jump to the left and come back? Why do we have to jump to the right and come back? Here's the actual definition of a limit. The limit. Not just the one from the left, not just the one from the right. The limit has this answer. Only if and only if. This was the answer that I got as I did the limit from the left. And this was the answer that I got as I did the limit from the right. So I jumped to the left, I found out where they were headed, answer. I jumped to the right, I found out where my y's were headed, answer. Do these two match? If they do, well then the limit of f as x approaches a must be this answer. So there's kind of three different types of limits. We've got the limit from the left, we've got the limit from the right, and we've got the limit. Let's try some. Okay, I've highlighted these so that the limit as x approaches 1, here's where 1 is. We just have to go find our function. Ready? Here I go. This says the limit as x approaches 1 from the left. So here's 1. Ready? I'm going to jump to the left of it a bit, and I'm going to go find the function. Here it is. Now, here I go. I'm going to work my way back toward 1, and I'm going to see where is the height of my graph headed as I work my way back. I think the height of my graph is headed toward this height, which is 1. Let's do this one. The limit as x approaches 1 from the right. Here's 1. Jump to the right. Go find the function. So here's the function. Here's the height of the graph. Come back. Come back until your eyes are here. So here's the height. Here's the height. Come back, come back, come back. Where are my y's headed? Well, that sounds silly, right? They're staying at 2, but that's okay. Where are my y's headed? 2, 2, 2, 2, 2. My y's stay at 2, so that's a 2. Now, the limit. Not the left, not the right. The limit. What's the answer to the limit? Do these match? Nope. The limit does not exist. Make sure that looks like a D, not an O. Okay? The limit doesn't exist. So what that means is, as x gets close to 1, were my y's coming together? No. My y's weren't coming together. They were like disjointed, right? They were like, no, they're far apart from each other. And then, just for fun, even though I said it doesn't matter, just for fun, is there a point at 1 comma something? Yeah, there's a point at 1 comma 2. That was just for fun. Doesn't really matter when we're doing limits. Moving on. Still looking at 1, new graph. The limit as x approaches 1 from the left. Here's 1, jump to the left. Where do my y's look like they're headed? So I'm coming back toward 1. The graph gets lower and lower and lower. I think my y's are headed to about a little less than 1, don't you think? Or negative 1. I don't know, like negative 1.1-ish, whatever. From the right, the limit as x approaches 1 from the right. Here's 1, jump to the right. Where are my y's headed? I think my y's are headed toward 1. the limit. Does the left and the right limits match? No. Does not exist. Is there a point at 1 comma something? Yeah. 1 comma 0. Okay, still looking at 1, different graph. The limit as x approaches 1 from the left. Here's 1, jump to the left, come back. Where are my y's headed? As I come back, my y's are getting bigger and bigger and bigger, and I think they're headed toward positive 1. From the right, come back, where are my y's headed? Y's are headed toward positive 1. The limit. Do they match? Yes. What that means is the function, the y's were coming together, right? They were headed toward the same spot. Did they ever meet? No, there's a hole there. They never met. There's a hole there. But they got really, really, really close on both sides. And then f of 1. Is there a point at f of 1? No. F of 1 does not exist. Okay, same deal. X approaches 1, y's are headed toward 1. Sorry, x approaches 1 from the left, y's are headed toward 1. X approaches 1 from the right, y's are headed toward 1. Check, check. Do they match? Yes. Is there a point there? Well, there's a point somewhere. There's a point at 1 comma negative 2. Okay, I'm going to speed up a little bit, make this go quicker. From the left, y's are headed toward 1. Limit from the right, y's are headed toward 1. Do they match? Yes, the limit is 1. Is there a point there? Yes, 0 comma 1. Huh. That's the first time that all 4 answers have matched. That will come up later. Not in this video. Next question. Now we're looking at positive 2. I've highlighted it for you. This is where your eyes need to be, okay? From the left, jump to the left. As I move closer and closer and closer to where are my y's headed? Well, the way that I interpret this graph, I think it keeps going, don't you? So as I get closer and closer to this asymptote, where are my y's headed? Well, my y's just keep getting bigger and bigger and bigger. My y's are headed to positive infinity. From the right, here's 2, jump to the right. Come back, where are my y's headed? Oh, my y's are headed lower, 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 lower. I think my y's are headed to negative infinity. Do they match? No, they do not. Is there a point at 2 comma something? No, there is not. Negative 2. Here's where your eyes need to be. From the left, positive infinity. From the right, positive infinity. Do they match? Yes, they do. Is there a point there? No, there is not. From the left, from the right, do they match? Is there a point there? Yes, there is. Alrighty, one more thing. Check this out. Let's do limits at infinity. So now, we're not doing as x approaches some number. We're doing as x approaches infinity. Remember, this tells you where your eyes need to look. This says, how high is your function? When you look here, how high is your function? So, let's just do some. Hopefully I can explain it well enough we don't need to look at any definitions. Ready? Okay. As x approaches positive infinity. Now I've been highlighting these, telling you where to look. Well, as x approaches infinity, I'm not going to tell you to look here. or here or here. I'm going to tell you to look where x is super large, super large. So I want your eyes to be way out here, way out here. Go find your function. Where is this graph? Where is this graph? Way out here. It's way up there. Ready? Next one. As x approaches negative infinity. This tells you where to put your eyes. Put your eyes negative infinity. I want your eyes way out there. Way out there. Where's your function? Way out here, your function is way up there. Okay? Now, I'm not doing the limit from the left and the limit from the right because we're not narrowing in on a function. We're looking way left or we're looking way right. We're not comparing the two. That's weird. That would be totally weird. Ready? As x approaches positive infinity, this looks like maybe a cubit. As x approaches positive infinity, look way out here. Where is the function? Way down here. As x approaches negative infinity, look way this way. Where's the function? Way up there. Next one. I believe this is a horizontal asymptote, and I believe this is a horizontal asymptote. Okay. So as x approaches positive infinity, ready? Take your eyes, you need to go way out here. Way, way, way out here. How high is my graph getting? Well, you know what an asymptote does. A function just gets super, super, super close to its asymptote, doesn't it? So I think my y's are getting super close to 1. That's what a limit's all about. Do they ever reach 1? I don't know, and I don't care. As x gets here, as x gets close to here, what is y getting close to? It's getting close to 1. Look way left. So eyes go way out here. Way out here. How high is my graph? What are my y's getting super, super close to? They're getting super, super close to this asymptote. -1. Okay? Oh, last one. Positive infinity. So look way out here. Notice how my oscillations, my bounces, how the graph bounces, get smaller and smaller and smaller and teeny, 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 tiny, teeny, tiny. So as I go way out here, do you think my y values, which used to be way up here and way down here and then here and then here and here and here and here, are my y values getting closer to one specific value? I think they are. I think my y values are getting closer and closer and closer to 0. They're going to be a little bit above 0 and then a little bit below 0 and then a little less above and less below and less above and less below. But yeah, they're narrowing in on 0. Same this way. The bounces, the oscillations are getting smaller. It's going to be above and then below and then above and then below and then above. It's getting close to 0.